we can interpret the real and imaginary parts of a complex number as x and y coordinates. Thus, we can interpret a complex number as a point in the plane. And in this context, we'd call it the complex plane. So here, the complex number z is represented as a point. Its x-coordinate is its real part, and its y-coordinate is its imaginary part. Once we've interpreted complex numbers as points in the plane, we can take advantage of geometric properties like length and distance. So we define the absolute value of a complex number to be the length of the line segment between that complex number, represented as a point, and the origin. That is, it's the distance between that point and the origin. In math, we would write it with vertical bars, and in Python, the absolute value of a complex number is written abs of complex number z. Given the input, it adds a complex number z0 to the input. And a translation can move the picture anywhere in the complex plane. All right, so we can interpret the complex number z0 as representing the translation that adds z0 to the input. Once we interpret a complex number as a translation, we can think of it as an arrow in the complex plane. The arrow's tail can be located at any point z. Then the arrow's head is located at z plus z0. So the arrow shows an example of how the translation acts on a point. So let's try representing this complex number as an arrow. We can choose anywhere to put its tail, and one convenient place to put it is at the origin. So the tail will be here. And the head should be at the location with x-coordinate -6 and y-coordinate 5. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So the head should be here. So the arrow would look like that. Now, consider two complex numbers. Each of them corresponds to a translation. Let's take the functional composition of those two translations. So first we apply f2 to the input, then we apply f1. That's the same as adding first z2 and then z1. So we can represent functional composition by adding arrows. Here's an example. Let's say we're first going to apply f2. So that takes a point. Let's start with the origin and translates it 3 units to the right and 1 unit up. 1, 2, 3, 1. So that goes here. Next, we'll write down the arrow representing this complex number. This complex number says move 2 units to the right and 3 units up. Now we can write it as an arrow with the tail located anywhere, and a convenient place to put the tail is at the head of the last arrow. So we're going to put it right here. Here's the tail. The head will be 2 units to the right and 3 units up. So this arrow is represented, this complex number is represented by this arrow. Now, what about the functional composition? The functional composition adds z1 plus z2 to its input. We can find that arrow by choosing its tail to be the tail of the first arrow and its head to be the head of the second arrow. So z1 plus z2 is represented by this arrow. So we see that addition of complex numbers can be represented by putting arrows together, adding them in this way. Consider the operation of multiplying a complex number by 0.5. What's the geometric interpretation? How does this affect arrows representing complex numbers? So we're applying the function f of z equals 0.5 times z. Let's say we start with the complex number 2 plus 4i. We represent that by an arrow that moves 2 units to the right and 1, 2, 3, 4 units up. So this arrow. When we multiply the complex number by 0.5, what we're doing is multiplying the real part by 0.5, halving the real part, and halving the imaginary part. As a consequence, the arrow representing that complex number goes 1 unit to the right and 2 units up. It gives you an arrow in the same direction, but half the length. This is called scaling. What about if we multiply a complex number by -1? Let's try that. Let's start with the same complex number, 2 plus 4i. Multiplying this by -1 means multiplying the real part by -1 and the imaginary part by -1. So we end up with -2 plus -4i, which is an arrow that goes in exactly the opposite direction.